maybe I'd get 5 people in the room, so I do appreciate your attendance, and I am delighted to be here. A little bit of more background about me, just so you have a little bit of context. Some of the moments I'm most proud of when I was at the IBM, maybe proud is not the right word, but fun, was you guys all remember Jeopardy and IBM Watson, yes?
Yes.
Okay, and I had the good fortune to work with Dave Ferrucci, who was our chief architect, chief scientist for Watson, and I also had the good fortune to, the day after, literally the day after, go on ABC News, do a TED Talk, and talk about the future of Watson. So that was a fun moment. The conversation I wanted to have with you today is about cognitive applications, and we're going to start that conversation, and I know I have a clicker, by giving you a bit of a history lesson, because I think the history lesson is important to understand where we've been as a guidepost and North Star to where we're going. So I'm going to discuss several things so you don't walk out of the room if you're bored with my history lesson. But I want to talk about AI, this concept of weak and strong. I want to talk about explainable AI, but you'll notice I have a conversation as well distinguishing predictive analytics versus machine learning, because I think we often conflate the two because the relationship between the two is so tight. The reason I think that distinction is important, because we are seeing the emergence of machine learning software engineering. We are seeing technical debt, which I'll explain, arise as we do more machine learning. So I wanted to explore some of those concepts. So let's get started. The picture that you're seeing is the history lesson. I promise I'm only going to spend about 5 minutes on this, but I thought it was important to give this lesson. Some of you who have the gray hair, maybe you weren't programming in the 60s, but you certainly are aware that in the 60s, just think about what was happening in our world at that point in time. We were early in the computer era. We were early in both what we did about software. In fact, if you go back to the 60s, it was hard to find a computer science program at the universities. It was all about hardware, all about electrical engineering. So what did we have at that point? We had mainframes, we had minis. What did we do? We built tons of back office systems, many of which, by the way, TOPS are used here today. Those systems used technology that we built in the 60s and 70s, KICS, DB2, IMS, COBOL. You remember, some of you, those technologies. So our first inflection point of change, by the way, occurred in the 80s. That was the microprocessor, the PC, a huge era emerged. But what I want you to understand is the way we built systems changed as well. So we went from these monolithic applications, centralized computing, to begin to see more. Not that we didn't have distributed computing prior, we did, but we saw more distributed computing. We saw 2-tiered architectures, 3-tiered architectures emerge. So we saw profound shifts. We also saw profound shifts in enterprises. We saw some tech companies, we saw their demise. We saw others rise, particularly in the 80s. The two most notable companies were Apple and Microsoft. And then, of course, the next inflection point came, which was in the 90s. And the reason I want you to pay attention to these inflection points is because I'm going to assert that we're in an inflection point right now. But I'll get to that in a moment. So this third inflection point, this third era, occurred with the internet. We often conflate the World Wide Web and the internet as the same thing, but one is an application and the other is not. The reason that distinction is important is because in the fourth era, we actually have the same thing going on with the Internet of Things. I sort of equate, it's not the same of course, the IoT sort of being analogous to the internet. If we go back into the early days of the internet, before the World Wide Web was even created, and even once it was created, there were significant players in the industry, Bill Gates being one of them, and others who saw no opportunity and no future for the internet. They thought it was a place of socialization and game playing, but no one saw Facebook, no one saw Amazon. And it tells us that, we can see from a distance a rainbow, but we're in the mist. It's really hard to see these things. So that brings us to the point in time that we're in right now. And the point in time we're in right now, if you pay any attention to the World Economic Forum, you've heard them talk about the fourth industrial revolution. You've heard them discuss the fact that the way we live, the way we work, the way we play will fundamentally change. And if you think that 2017 is 1990, that's about where we are. We're at the very early stages of this inflection point. And I say that because we don't have a killer app for IoT right now. We don't have killer apps for cognitive systems right now, but we're getting there. So we'll come back to that concept in a moment. So the point I also wanted to make clear here is when you look at this picture, you'll notice in cognitive systems, there's several things I talk about. It's not any one of these technologies that's bringing about this shift. It's the actual intersection of all of these technologies: social computing, mobile, the modalities of voice, the advances that we're seeing in artificial intelligence. So this notion that data is the new oil was coined by a mathematician in the UK, I think a decade ago. But it really is the new natural resource. And it is the oil of the internet, it's the currency of digital, and it's the heart of cognitive systems. And when we think about cloud, cloud is the consumption and delivery model for cognitive systems. It doesn't mean that it's the only way to do it, but cognitive systems exploit cloud services. It's an underpinning technology to make it ambient, to make it cognitive. And we'll come back to those terms in a moment. So this enabling of ambient computing is a future state, a state where we will live where the presence of digitization, the presence of electronics, the presence of things will sense our presence and operate and respond accordingly. So all the stuff that we see in the movies has a great potential to come to fruition, maybe not fully in all of our lifetimes, but certainly in the lifetime of our children. So IoT is bringing this volume of data that has been unimaginable. And this picture is just trying to emphasize that we do have this explosion of data that is upon us. It's coming from sensors, it's coming from robotics, it's coming from devices, but more importantly, it's creating these centers of gravity around data that we find in hospitals, we find in networks, exchanges, we find in our own data centers. So we're seeing this centers of data emerge, and today they're highly isolated, whether they're in your home, whether it's in a provider location. But the message here is that we do have this enormous amount of centers of data. We're also beginning to see this merger of, I think one of my words got missed there, I apologize. But what it's meant to say is that when you think about information technology, which is the world that most of us play in, whether it's on the business side, whether it's on the technology side, there's also the world of operation technology. The stuff that you actually, the medical devices, the equipment that you see in a hospital or a factory floor. And we're beginning to see the merger of these two worlds. And why you see the metaphor of the horse and buggy and car in this picture is it reflects the shift that's occurring in pretty much every enterprise. That shift that's occurring in every enterprise is that we still have the old and we now have the new. We're seeing that in both skill sets and in the type of applications. So again, my point is that even when we look at the prior eras, we saw this duality. We saw the presence of both non-client server applications and client server applications. And we'll see that now. It's going to be a ways before we're at the point where we only see one of these things. So there's not an agreed upon definition as to what are cognitive computing or cognitive systems. And I don't want to get into that debate, but I do want to just offer up that I think that what I've offered here, we tend to, as an industry, to agree. There's some nuances that we can debate, but the point of this is that, and I'm making the distinction between computing, which is really going to be the technology that we leverage, whether it's machine learning libraries, whether it's GPUs. There's all of this compute power that is being built by all of the big players. And by the way, if it's not obvious to you, we've seen a shift in computing as well because of this new era. If you had an opportunity to look at the MIT magazine recently where it listed the top, or the 50 smartest companies, NVIDIA, a company that a lot of people haven't even heard of, but NVIDIA, I think, ranked #1 in that list. But many people look at NVIDIA as a hardware company. We had an opportunity, several people on my team, to just literally 3 weeks ago to meet with Jensen, who's the CEO of NVIDIA. They're a software company as well. And the explosion of work that they're doing, the fantastic work they're doing, and they're not isolated. This work is being done by a lot of vendors. But my message here is simply that we're in the very early stages. Let's take a quick look at deep learning, for example. You know, arguably, when you think about everyone, maybe not everyone, but most of us believe that deep learning, which is a subset of machine learning, is going to revolutionize healthcare. The most dominant examples, I would argue, assert around deep learning have been with autonomous driving vehicles. That's where we see it. And, you know, I read an article said, well, you know, it talked about using GPS and maps, but that is not what's causing those cars to be autonomous. They literally are using machine learning. They're using deep learning. The reason I wanted to mention it is that, you know, arguably, we had a very low bar to set here, a very low bar. When you think about our ability to detect images, to detect that this is a person versus a billboard, that something is moving, that this is a cat versus a muffin, very low bar. And so it's gotten a lot of excitement. What's a high bar? I would argue that the problems that we face in UHG are some really hard problems. We have probably in this room, I know Josh is an emerging data scientist, but we have a lot of data scientists, both experienced, like Roland and others, but the point I'm making is that to apply the same kind of revolution in cars into healthcare is going to require all of us to participate and think about how we make the customer experience better, how we make the healthcare system a learning healthcare system. So these are big problems that are, I would assert, more challenging than an autonomous driving vehicle. But we'll learn lessons from those folks as well. So what's a cognitive system? I'm asserting, and I'm using these words interchangeably, a cognitive system, an intelligent system. I think they're interchangeable. I'm not trying to make that distinction. I'm simply trying to assert that a cognitive system is one that does adapt, that does learn. In some cases, it may generate software, generate programs. It will use algorithms. I heard, or you know, some would assert that algorithms is Latin for software made me do it, but algorithms will become more powerful. So cognitive computing, it says, and I think this is true, we'll redefine the relationship between us and our environments. So let's have just a short conversation about artificial intelligence. Let me give a quick disclaimer. This picture is not scientifically accurate. It is not technically accurate. It's really trying to convey the following message. It's simply trying to say, don't think of artificial intelligence in a binary form. Think about it on a continuum. So let's take Elon Musk, for example. Elon Musk, you may have heard, has increasingly stepped up his game in terms of his assertion that artificial intelligence is an existential threat to the species. He upped his game just recently, said it's going to cause World War III. So whether he's correct or incorrect, I would assert that, let's look at the science here for a moment. Clearly, every tool that we create as a species can be used in a variety of ways. It can be weaponized. It could be used for the good of mankind. That's a choice we make as a species. I would assert it's not AI that's doing it. And I know some of the fear arises from the black box concepts that evolve out of deep learning. And there's some good reasons here. We'll talk about that in a moment when we talk about explainable AI. But the point I'm getting at here is that there's a continuum here. Those of you familiar with the Turing test by Alan Turing, you know that we're not there yet. We don't have strong AI. We don't have the ability to do what we see in movies right now. It's simply not there. And when will it be there? Some of the outstanding thinkers in this field think that, Ray, I always pronounce his last name incorrectly, Ray Kurzweil?
Ray Kurzweil.
Kurzweil? Yeah. Ray has, I think, lowered his projection from 2045 around singularity to 2029. So he's very optimistic that we're getting there sooner versus later. But the message of this slide is that we're really far to the left right now of weak AI. And that's not a bad thing. And if you think about the advances in deep learning, most of those have occurred since 2010. What happens when we have another decade behind us? What will we see? What will we be able to do? I would assert it's going to be pretty amazing that we're at the early stages of invention and we have a lot of opportunity. So this is, again, one of these areas when we talk about building cognitive systems that we're going to have to keep our pulse, our eye on the what's happening in the technology arena. So the key messages here are that we've seen some remarkable things in vision, in cancer detection as an example, where we can now detect, or we can use computers now and software to have a better accuracy than humans in many cases. So there's some amazing things occurring as we see with natural language processing and voice and imaging and so forth. This notion of explainable AI is an interesting one because we had an opportunity, as I mentioned previously, to engage with NVIDIA and their CEO. And he didn't use the term explainable AI, he talked about testable AI. And basically he and his team, they were working on methods and techniques to really try to understand why an outcome was being achieved. So if you look at this picture for a moment, the scenario we have today is we have this training set, we do some work with neural networks, we produce an output, in this case maybe a probability of 93% accuracy. This is a cat. And do we know how that happened? How did we get 93%? Why was it not 96%? Why was it not 87%? These questions are questions that, to be blunt, we can't explain unless we plan to explain them. So the scenario you see at the bottom says we also have to think about this explainable model. We actually have to build in techniques and methods to begin to understand why we're getting the result we're getting. I suspect that in our industry, that doctors are simply, not just doctors, executives, patients, we're just not going to be satisfied that you say that my chances of getting cancer are 98%. We're going to say, tell me why. And it's got to be explainable. Or so this explainable AI, there's a lot of interesting developments occurring in this space, but it's an area that, as we think about software engineering, that we're going to have to explore. So this may be a contentious slide, but that's a good thing. We want to be provocative. And what I want to illustrate on this slide, and I welcome your feedback on this, I created this and I think this is fairly accurate, is that we do have this, I would assert, a distinction between analytics, which our industry, and particularly UHG, is extremely strong in. We've got great mathematicians, great statisticians, excellent software engineers, and the point I'm making is that these two are so tightly coupled, machine learning and analytics, that we often conflate the two. If you go back a little bit in time, we never conflated a data modeler with a database administrator. We sort of understood that a data model was an abstraction that we used to ultimately generate and create databases. We had skill sets to create the model, and we had different skill sets to perform, to generate, tune, and create the databases. And we never conflate, maybe we did at one time, but the point is, we understood the differences. Those two parties had to work hand in hand. It's quite possible in many cases a DBA didn't have the skill to create a data model, but he certainly knew how to, or she knew how to read a data model, and the data modeler may not have had the skills to do database administration. In a like manner, we have folks who are data scientists who are awesome. They create fantastic models. Those models in some early cases were if-then-else logic, this decision tree logic. Tomorrow, they're machine learning models that use training sets. But the point is that there's this distinction between the two. So why does that matter, you say? Kerrie, who cares? And I would argue the reason we care is because data scientists must now understand software engineers, and software engineers must understand data scientists. And again, you're asking the question, who cares, Kerrie? You haven't answered the basic question. Why does it matter that these two work? I mean, of course they work together, but who cares? And that brings us to the conversation around technical debt. So, what is technical debt? Let's just understand a few things. Every software program that we write, if it gets used, it will change. I think we can agree on that. Software entropy is increased with the accumulation of technical debt. What do I mean by that? I mean chaos, I mean disorder, I mean the inability to use that product in the future. Stated differently, the inability of business to have an application change on demand when it wants to. The inability of a business to say, I want these 5 fields and I want it in 3 hours. I don't want it in 6 months, and I don't want it to cost me $500,000. That's the state of our affairs today. And that's because this is what happened to software. In case you don't know this, in our industry right now, in our industry today, and I'm being conservative in the time frames I'm going to give you, within 3 years, many of my colleagues would assert 1 year, but I'm going to go 3. Within 3 years after building products and putting them into production, those products become brittle. That's max 3 years. Think about what happens when you build things. There's always this technical debt. So technical debt, you see I'm equating it to a credit card. So you can buy things on credit, but sooner or later the bill comes due and you have to pay up. So how does that equate to software? In software, we incur these bills by our decision making. We may also incur them because of business pressures, time pressures, schedule pressure. We may incur them because of lack of skills. We may incur them because we don't adhere to standards. We may incur them for a numerous set of reasons. But the point is, we're getting a debt here that's accruing gradually. And we have an opportunity. We have an opportunity because we're at the early stages of cognitive systems to maybe stop incurring so much debt. I don't know if we can get to 0, but we can certainly do better than we've done in the past. And you may ask, why can we do better in the past? That would be a more detailed conversation. But I would assert that the underpinning of cognitive systems are a variety of technologies. You may or may not have heard a term called situational applications, or there's another term, I forget it at the moment, but the message I'm trying to communicate is that with cognitive systems, we should be at a point where, in some cases, it's okay that they have a short life, that a cognitive system has been built to scale, it's been built to perform, but we'll throw it away in 3 months if something better comes along. And as long as we can build fast, that's okay. As long as we can build sustainable cognitive systems fast, it's okay to throw away systems. This is a different mindset than we've had in the past. But even though we throw things away, it's like kids who build Lego pieces. We have struggled as an industry to get to that metaphor of being able to build sustainable systems the same way kids build new structures with Lego blocks. But with cognitive systems, one of the imperatives of cognitive systems is that they be consumed and delivered. Not that they have to be, they should be able to be consumed and delivered as services. That means cloud services. They should be consumable that way. What does this mean? It means that we have to embrace APIs as a means of consumption, as a means of orchestration, as a means of building. It means we have to embrace microservices. What are microservices at the root? Microservices are not APIs. Microservices are fundamentally different. But what are microservices? They're deployment units. They're in effect Lego blocks. They are the things that we assemble. Whether we assemble them on the edge or whether we assemble them in the cloud, it doesn't matter. The point is, and this goes back to the debt issue again, when you think about building cognitive systems and think about building software, the reason that things take so long to build, most people think it takes long to build things because of coding. But it's actually not coding at all. Coding is the fastest thing we do as an industry. The two problems we have in building things happens on the front end and on the back end. The front end is figuring out what to do, agreeing. The front end also includes going into those systems where we have to refactor things, where we have to do impact analysis. That takes enormous amount of time. And the other side of the coin is on testing. We don't have the systems we build today, even prior to cognitive, we don't have the cycles. We don't have the manpower to test those systems. So in order to eliminate those two cycles, we have to do things differently. So I'm simply asserting that this is an attribute of cognitive systems, that we actually build them differently, we think about them differently, and there's a great article by Google. The reason I pointed out this Google paper is because as an organization, I would assert we're in the early stages of applying deep learning. What we can learn from others who have been doing this, not decades, but for, let's say, 5, 7 years, what we can learn from them is the experience they've had in incurring technical debt. And this paper is, I would argue, is a pretty good paper to begin to see some of the issues. And there's a whole series of good articles in this space. I do think that one day, and I think this is definitely more than 10 years out, we will have a learning healthcare system. And a learning healthcare system will be built on cognitive applications. A learning healthcare system will be a system that exploits the Internet of Everything. It will have ambient computing. I will walk into a hospital room or be carried in a hospital room, and at some point when I'm awake, I will be able to use my voice to contact my family and friends. I will be able to see the state of my condition, whether I've got 2 hours left or I'm going to walk out of this hospital tomorrow. I'll know that. I won't have to engage with my doctor to tell me that. This is going to be the world where today I have a heart problem. I do, electrocardiograms. And because when I do them, I have to go into a hospital to do it, it doesn't quite catch the irregularity. But tomorrow, I'll be wearing a device that will capture that data. I won't do anything like, if you're an Apple Watch, a Fitbit, it'll be the same thing. This data will be synced automatically. Your doctor will have accessibility to it, and they will use it. The doctors will operate as you and I do in this ambient environment, whether we're talking about labs, just as today. I mean, if you think about our world, 30 years ago, we didn't have mobile devices. And my children today want to know, how did you contact your friends? How did you make a travel reservation? Think about what the kids are going to be asking when this world comes to play. But in order to build this world, we have to understand that we are at the early stages of IoT. We're at the early stages of AI. Give us another 20 years, and we're going to see some fantastic things. But we don't have to wait 20 years to make a difference here at UHG. We can start today building systems that create better customer experience, help us scale as we grow our members without incurring thousands of people in our call centers. So this is a vision, I would simply assert. But in order to get there, we have to understand that, that how we do processing has to change, and it is changing. So what you're seeing in this picture is simply reflecting the fact that we're going to have multiple computing models. We're going to have what we've done in the past, which is where we take data and we send it to the computing resources that we have. But we're going to see more of the model at the bottom where the processing power will be where the data is emanating from. That's IoT. That's the future and the present. We see it in the oil industry today. We see it in manufacturing today. And we see it in hospitals today as well. So we're going to see more and more of taking compute processing to data. And that's going to require we think about things differently. And we're going to see all of these tiered architectures come alive. We're going to see these 4-tiered architectures. Streaming analytics is going to be important. And think about Apple for the moment. There was a recent article, if you haven't read it, it's a fantastic article. It supposedly is a leaked article about what Apple is up to with AI. And what are they up to according to this article? It makes perfect sense. It simply says that Apple is looking to spend a lot more energy in terms of the compute power that you and I have in our phones. And why do they want more compute power? Because they want to have more deep learning running at the edge, in your pocket. Think about what Siri can do if it had that kind of compute power eligible to it. We already know, from a research standpoint, we already know, I mean, we see it every day. The amount of compute power in our phones is greater than we had in the 50s. But the research that's going on around AI is incredible. So look for more in this space. And I wanted to, and I think this is my last slide, but I wanted to sort of summarize by saying that in the past, when we think of applications, we've always thought of them as this singularity thing. We build it, but I think when we talk about cognitive systems, there's no longer the single location notion. A cognitive system will live and be made up of many parts. It will have this particular model, if you're curious about it, is something I simply took from the IoT reference model. So it is an IoT reference model. But I think when you look at this model, what you see, and I've manipulated it a bit, we're going to see model training occur most likely for the foreseeable future, still at the data center where the massive compute power to take massive amount of data lives. So we won't see that at the edge. You know, the model training doesn't occur in an autonomous car. The model is pushed at runtime, it's pushed for deployment and operated at runtime. So we're going to see the model training occur in data centers. We're going to see cognitive applications. We'll still have analytical applications as well. Remember, with these eras, nothing goes away. There's always this overlap that we see. And we're also going to see more model propagation, and we're going to see more edge computing. So this is going to require, when we talk about edge computing, again, we're talking about wearables. We're talking about things that are embedded in our body, the stuff that Medtronic produces, for example, to do heart monitoring. We're talking about our cars, our homes. All of these are examples of edge computing. And with that, I will take any questions. I know I'm about 10 minutes early, but any questions or comments or on any topic? Yes?
Since we are in the early stages